Hello, it's Keith here, and this is lesson 2 of the simple series of my PowerPC assembly programming tutorials, and we're looking at the GameCube, of course. Now, today's example, we're looking at the joypad, joystick. We are basically using two controllers here. One is moving the small one. This is the digital pad, I think. I'm using an emulator, so I'm using the cursor keys for both, but the other one is using analog. So we're moving two sprites, drawing two sprites. As I said in the last lesson, the simple series, lesson 1, there's an issue with drawing very small objects on the GameCube because the color information is shared between two neighboring pixels. So you can see maybe there that around the hairline of the Chibico character mascot there, that it's gone slightly blue rather than cyan, whereas on that one it's pure cyan. Maybe you can't tell, but anyway. Being as there's issues drawing the different sizes, I thought I'd draw both, and I thought I'd control both in different ways. So that's what we're looking at. We're running the example on Super G-Cube today, and the documentation I based this on was the YAGCD, yet another GameCube documentation. I say that because I'm doing the initialization routine, I think, as per specification. It didn't seem to matter if I did it or not, though, which my suspicion is that it probably means the emulator actually isn't fully emulating the hardware. I'm not saying the documentation is incorrect. I don't have anything better, so I assume it is. But as I say, I'm doing what it said, but it didn't seem to make a difference. Anyway, that's what we're going to be looking at today. So the example today is this one here, NGC joypad. Now this is a single ASM file and it will run and do what you just saw. However, there's a bit of an addition to this one, basically because I'm kind of combining two tutorials into one here. If you enable this option here, it will include another few ASM files. And the purpose of that is to show the text at the bottom of the screen here. And so now as I'm pressing the buttons, you can see this is the digital, so you can see individual bits are changing. And then here is the analog, so you can see that's going from 0 to FF, and 80 is the sort of dead zone center. So that's just so you can test the individual keys, and I'm sure there's the fire buttons and things. So just as an additional one, because I'm not doing a second tutorial just on the joypad, so it's all in one. Anyway, as I say, if you're using a different assembler, if you just remove the parts that use that if-def, it will work fine on its own. Okay, so if you need to know how to build an ASM file, I'm using ELF to DOL to convert the DOL file for the emulator. That's in the Hello World series, so please see that if you need to know how to build your file. And at the start here, what we're doing here is we are setting the memory address of the VRAM. So basically we are setting the VRAM to that address there. The C at the start of that sequence there, that means we're going through the cache and a cache through address. And so that's the VRAM address we're setting up there. We're using a CLS routine here, which is just writing all of the pixels of the screen to black. We're drawing the sprites to the screen, and then we're initializing the joypad, and then we drop into the main loop, which we will look at in just a moment. Okay, well, at the bottom of the file, let's take a look at what we've got here. Well, we're defining some longs here. These are some 32-bit values for the X and Y position of both of the sprites. Two sprites, so two XY positions here. We've got some offsets defined here because we're going to use the offset addressing to get to those. Okay. Now we will look at the drawing routines first. So when we want to clear the screen, basically all we do is we clear all of the bytes of the screen. That's the start of the screen memory. The screen is 640 by 480, and there's 2 bytes per pixel, but we're writing in words here, 32-bit words here. So this is 320 by 480 words, and so that's the amount that we're having to actually do there. So that's going to clear the screen, and we're just writing the colors here, the color black here, because of the weird memory layout of the screen. You have two bytes for the color information there. 80 is basically grayscale, and the brightness for the 2 pixels is here. That was covered in the bitmap example, the previous simple example series, example 1. So if you need to see that, please check that out. Okay, so that's clearing the screen. We have a very similar routine called fill area here. All this does is it fills a block of pixels with a single solid color. I'm not going to cover that because the code is almost identical to the draw sprite routines, which we will look at. Here they are. Here's the draw sprite 1 times routine. So this is going to draw the unscaled sprite to the screen. So we're going to basically read in information as is and write it to the screen. So basically we've got our X width in R5 here, so moving that into the count register. R4 is going to be our VRAM destination, so we're moving that into R8 for each line. So we're reading in a 32-bit word from R3 here into R0, and then we're storing that to the screen here. After each 32-bit value, that's 2 pixels, has been drawn, we're moving across the screen memory and the source bitmap data. We're repeating for the entire line of the screen, so we're drawing across, and then we're going to jump back next. So we jump back by basically moving the VRAM destination in R4 down a line. And remember, we moved R4 into R8, so we were working on a copy there. So we've now moved down one line, and then we decrease the Y count and we repeat. So that's the 1x version. And the only difference between that and the fill version is basically the fill version's writing the same 32-bit value every time, exactly the same code otherwise. The 2x, the double-scaled version, is slightly different. Now, the source bitmap data has been scaled horizontally by 2x, so that was done by my Sprite editor. It's free, it's open source, and that can export in various formats. So that has doubled the horizontal width of the bitmap data into the binary. So the colors are preserved, but it doesn't vertically do it because we just write the same data twice, and that's the difference between the two versions. So here we are reading in a byte from R3, that's our source bitmap data, but we write that to the screen twice, once to offset 0 and then once to offset 1 to 80. 640 pixels on a screen, 2 bytes per pixel, 1 to 80 moves us down one full line. So we're writing the same bitmap data to 2 consecutive lines. So we're just repeating till we've done a line. Once we've done a line, we move down 2 lines because we've drawn 2 lines. And so we add 1 to 80 times 2. And we repeat for the remaining lines of the bitmap. There we go. So that's what we're doing there. Now, these routines are used in 2 routines. So we've got this remove sprites routine. And what this does is it loads in the XY position of the 2 sprites. We're loading R10 with the base of the user RAM, and then we're using those offsets that are defined, and we're loading the X and Y position, and we're using get screen pos to calculate the VRAM address, and then we're using fill area here. This is removing the sprites, and we have drawing the sprites, which is exactly the same. We're just using the bitmap routines instead of the clearing routines here, and we're loading the width and the height here as required. Get screen pos, very straightforward. So we're taking the VRAM base here, that's that address here, that's a start. And we're taking the Y position and we're multiplying it by the bytes per line, 640 pixels, 2 bytes per pixel. So that's why we're multiplying by that value there. And then we're taking the X and we're multiplying that to 2 bytes per pixel. We're adding those all together and that gets us our VRAM destination for the screen memory. So very straightforward there. Okay. So those are the routines we're using to do our drawing. The last one we're going to discuss is joy init. And if you need to see more about those, please see the Simple Series episode 1, because I covered that there. Okay, so here is the initialization as I understand it, because as I say, didn't actually seem to make any difference if I did it or not. But it makes this is very logical what it's doing. This is the kind of thing you see in other systems. So we're using what's known as the serial interface, and the base memory address of that serial interface is this address here. And so we're going to use various offsets to that. Now the first one, we're sending a command. Now this is, I think, is kind of like a fixed value here. So we're writing this value here to offset 0, which is that register there. So that, I guess, is some kind of initialization command. And then we need to set the bits for the pads to turn them on. Now, I'm setting all the bits to 1 here. That should turn all the pads on there. That's what we're doing there. So I'm only using 1, but technically it has 4. So we're turning all those on there. And then what we're doing here is we're writing a value at 0. Now, I'm being a bit excessive here. I've done all the 32-bit values as full parts. I know I could have done that shorter, but just for clarity, I'd like to be able to see everything very clearly. So we're storing a 32-bit 0 to offset 80 here, and that is the buffer. We're clearing the buffer, basically. Now, what we then need to do is we need to wait for the hardware to become ready. So we're checking the status register, and we're checking the very top bit of the 32-bit value there. Now, when that goes to a 0, that basically means the hardware is ready. What we then do is we write a value 1 to that same bit, and we write that back to the same register. So that is, I believe, the correct initialization routine, as I understand it. But as I say, it kind of didn't make any difference whether I did it or not, which is rather a surprise, really. Anyway, so with this emulator, like I say, I know it's a very crude emulator, but it was the only one I could get working quickly enough for these tutorials. A lot of the emulator, getting working examples on a complex system like the GameCube wasn't very easy within the time constraints I have for writing these tutorials. So I was only able to get this sort of relatively simple one working. Anyway, when it comes to reading in the directions, it's actually very, very straightforward. So we have 2 addresses here that we read in from. So there's this one here and there's this one here, and we just read these in, and the various bits provide the various functionality. So we're going to use up, down, left and right, and we're going to use the analog X and Y out. I think it's this one we're using, the X and Y. There's a second one here for I forget the GameCube. It's the weirdest controller I've ever seen. Anyway, so here we're showing them to the screen if that functionality is enabled. But and other than that, what we're going to do is we're basically going to load those two joystick registers into R3 and R4, and we're going to load our directions into R11, R12, R13, and R14. And we're going to then process the directions, and we're going to potentially move those sprites. So what we're going to do is we're going to test each direction on the joystick, and if that's being pressed, we're then going to test the position of the sprite, so if that's our sprite. Because if the sprite is at the far right of the screen and the user's pressing right, we don't want to do anything. But if the user's not at the far right of the screen, we want to move the sprite to the right. So that's what we're going to do, and we're going to do this for every direction, one after the other. Now, this is a very crude routine. The clearing and the sprite drawing and clearing is very crude. So all we're doing here is we're removing both the sprites and drawing both the sprites. We're using R15 as a flag for if any drawing needs occurring. If we didn't do that, we would get some slight flicker because of how crude these routines are. Again, the GameCube is a 3D, very, very powerful piece of hardware, and I'm doing this in an extremely crude way. This is simply because the PowerPC is the last of priorities on my list of things to do, of systems I ever wanted to cover. So I'm not really putting much time into writing these tutorials, truth be told. I was originally only going to do the Z80 when I wrote these tutorials, and that was 15 processors ago, so you'll have to excuse me. Anyway, so that's the procedure. So what we're doing here is we're loading a test value into R6 with a single bit set. Now we're going to test these bits one by one. And so we're going to test the first one. The first one we're testing is L here. So we're doing this AND here. We don't want the resulting value. We just want the flag set. Now, if the bit isn't being pressed, we're going to skip down to here. But if the bit is being pressed, what we now want to do is we want to consider the left position of our sprite. And is the left position already at the far left of the screen, position 0? If it is, well, we can't do anything. But if it's not, we're going to subtract 2 from the X position, and we're going to set the flag to update the sprites. Okay, so that was the far left. We now do the far right. We're shifting the bit that we're testing 1 to the left. So before we were testing that L bit there, now we're testing the R bit. And we do the same. So is the direction pressed? Yes, it is. Well, is the player already at the far right of the screen? The screen is 640 pixels wide. The sprite is 48 pixels. So are they already there? And if they're not, well, we can move to the right by 2 there, and we repeat again. So that's what we're doing there. And then we do the same for down and for up. And so that's all of the directions for the first sprite. What we now do is the same for the second sprite. And I'm showing the wrong information there. That's not the joystick I'm actually using. So I'm a bit confused. I don't remember the GameCube joypad having 2 analog sticks, but maybe I'm wrong. I have one. It's the most unpleasant joypad I've ever seen in my life, but maybe I'm wrong and misunderstanding its capabilities. Anyway, so what we're going to do is we're going to mask basically one of the directions here. So FF here, we're going to test the X axis first. Those X bits, we're masking those, and we're going to basically have to work with a dead zone because our emulator actually gives 0 and 255, but a real joypad never would. So we're going to consider anything below a value of 40 in hexadecimal to be the left, and anything over C0 to be the right, and anything in between is nothing. So that's what we're doing here. But then apart from that, the procedure is identical. So we're testing the left, seeing if the sprite is at the far left, and we are subtracting again and setting the same flag if it is. And we do the same for the right and the top and the bottom there. So exactly the same procedure there. So we did the left bits there by using that mask, and then we use the up and down with that mask, and that's testing all the directions and updating the sprites. So our registers now contain the updated position for the sprites, but what we need to do first, what we do very first is we check if the flag is set. If it's not, then no directions have been pressed or the directions couldn't be moved, so we jump all the way back to our infinite loop, which is the main loop here. Repeat. If the directions have been pressed though, we remove the sprites from the screen using the old settings. We then update the settings here. You can see those settings being updated, and then we draw the new ones. And we've got a delay here. Now, quite curiously, this emulator is running an awful lot more slowly on this machine than my other one, which I don't quite understand. I've actually moved to Linux for my main machine now, so I'm actually doing it all through a Windows 7 virtual machine. The Windows 7 virtual machine seems to be faster. I don't know why that is. I don't see any reason that this computer's about the same speed for this purpose, at least anyway. So maybe the emulator just doesn't like this graphics hardware. Who knows? Anyway, Just some slight curiosity there. But anyway, that's this example. As I say, it's only a very simple one, but if it's any use to you, you're welcome to go to the website and download it. As I say, I very much doubt it would work on a modern emulator. I think the emulator I'm using is extremely simplistic. That was all I wanted. I was just looking to play with PowerPC. I don't want to program GameCube games. I don't have the time. So as I say, if it's any use to go to the website and download it and do whatever you can with it. I hope you've enjoyed this. This is probably going to be the last of the GameCube PowerPC tutorials, so I hope you have enjoyed them. So say I really can't go any further into it. I just don't have the time, and it's not the system that I ever wanted to be spending my time on. Anyway, I hope you've enjoyed what you've seen today. Thanks for watching, and goodbye.